Hello, in today's video we would like to say some words or introduction about uh, Cartesian product of two sets x and y. Now we know that if the set X has elements, say x1, x2, x3 dot 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 xn, while set Y has elements y1, y2, y3 dot 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 yn, then x cross y is the set termed to be the Cartesian product of x and y, whose elements may be written as the ordered pairs of x and y. That means we have xi, yj taken in all combinations, x1, y1, x1, y2, x1, y3 and so on with x1, yn, then x2, y1, x2, y2, x2, y3 dot 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 x2, yn. And similarly up to this xn point, when we take the combination of xn y1, xn comma y1, xn comma y2 dot dot dot, the last element is actually xn yn. We may write the first and last elements as starting with x1 y1 and ending with xn yn. So there are all possible combinations of the elements of x with those of y. Now, what is the utility of this Cartesian product of two sets x and y if we apply this concept to real life? I'd like to emphasize on the fact that if we consider the real line R and all the, let us take the real line and only the positive integers and negative integers on it. Let us denote the real line by R. So all the positive and negative integers are taken to be the members of this set R. So we may write them as plus minus a1, a2 and so on. So remember that this is an infinite set. So what will be R cross R according to the definition of Cartesian product? So we have all the linear combinations like this, a1, a2, a1, a3 and so on. Obviously we have a1, a1 as well as a2, a2 and all the possible combinations. So actually if we denote this R by x-axis and a perpendicular line by y-axis, then we have the R2 plane, so called two-dimensional coordinate plane. So here we may relate algebra with geometry with the concept of a mapping defined from R to R cross R. We may define a mapping from R to R cross R. Now we may go on taking this type of Cartesian products more than twice. We may think of this type of Cartesian product. This may be written or accepted as all the 3 points x1, x2, x3, and we know that this will represent geometrically the R3 plane, where xyz is usually the locus point of the plane. Any point in the R3 has 3 coordinates, and they may be taken as the Cartesian product of 3 R's. So what is the advantage of defining this type of Cartesian products? And the advantage is that on this set we can define function or mapping with which we include the algebraic properties or all the structural qualities of algebra and relate it to the geometry of 2-dimensional or 3-dimensional plane. As we know that if we take the Cartesian product of 4 R's, we have 4-dimensional plane which we cannot draw geometrically, and we can generalize this Cartesian product to n tuples also, isn't it so? Which is termed as Euclidean n space Rn, Euclidean space Rn, and a general member of this Rn may be represented as, we term it as n tuple x1, x2, x3 up to xn. So this is actually Cartesian product of real line n number of times. We have taken the Cartesian product. So this is termed as n tuple. So we can generalize the algebraic structure and we can relate this to a geometric structure. So our first task will be to endow this type of sets having n tuples. Let us begin with 2 and 3, R2 and R3, which we can easily comprehend, isn't it so? So if we map the set R to its Cartesian product R cross R like this, any integer is mapped to this point x comma 2x, we know that this represents the straight line y equal to 2x. If we put the function as this, that f maps x2 x comma x square, then we have parabola, isn't it so? We can as well map f of x to x comma 1 by x. Obviously this is represented as the y coordinate, and we have different geometric structures. Now this R or the real line has some beautiful properties which manifest itself with the properties of sequence of real numbers as well as the metric which introduces the distance. What is the distance between 2 points? In geometry we know that if we have in this 2-dimensional plane, if we have 2 points x1 y1 and x2 y2, x1 y1 and x2 y2, the distance between these 2 points is measured as root over x2 minus x1 whole square plus y2 minus y1 whole square. This is the geometry of the R2 as far as the geometric property of R2 is concerned. We define this distance as a measurement d, which satisfies 3 properties, that this is always, this d is always greater than or equal to 0, and if this d is equal to 0, then we have x1 equal to x2 and y2 equal to y1. That means both the points merge with each other. And we know that we have the famous triangle law where we say the distance between triangle law may be written as d of a point P1 plus d of a point P2 is always greater or equal to d of a point P3 if P1, P2, P3 are the length of the three triangles. This is the famous triangle law. And we have also the symmetric property where the distance between 2 points P1, P2 is always same. It is symmetric whether we measure it from P1 to P2 or we measure it from P2 to P1. So with the help of this distance measuring property, which we term as metric, we endow the real line with two properties. One is the concept of topology, open set, and concept of open set and closed set. Closed set is which contains its boundary, and open set is which do not contain its boundary, and all the boundary points are taken to be the limit points of the set. So with these two concepts, topological concept and metric, distance metric concept, we can relate this n tuple or R2, R3 points algebraically to the geometry of two-dimensional plane as well as the geometry of three-dimensional plane. And we can generalize this concept to Rn by writing member of this Rn as an n tuple x1, x2 dot 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 xn, and all the properties of boundedness, monotonicity, convergence can be extended to establish a relation between algebra and geometry.